All right, let's jump right into this explainer. If you've been building AI applications lately, you know all about RAG, right? Retrieval-Augmented Generation. But here is the harsh reality that usually costs developers weeks of painful debugging. RAG is not just taking a PDF, running some basic chunking, generating embeddings, and tossing the whole thing into a vector database. It's a highly disciplined engineering practice. It's really the art of building accurate, stable, and completely explainable knowledge systems. So today, we are going way beyond the surface.
This is saying I absolutely love right now. The hype is about RAG. The work is in the hidden layers. And that hits the nail on the head. Basic RAG pipelines, they work beautifully when you're following a weekend tutorial over perfectly clean, curated documents. But the second you deploy those toy apps into a real production environment, they break. They break in dozens of incredibly frustrating ways. To survive in production, you have to dig into those hidden layers and start using deeper, battle-tested architectural patterns. Here is our roadmap for today. We'll start with the surface trap, move into advanced retrieval mechanisms, tackle corrective and self-reflective RAG, explore graph and agentic innovation, and finally, tie it all together with the production realities. Part 1. The surface trap. When most developers say they're building RAG, they are operating entirely in what we call the surface layer. We're talking basic LangChain setups, simple text chunking, and standard vector databases like Pinecone or Chroma. Look, this is toy RAG. The deep layer, where real builder-level systems actually succeed, requires a completely different toolkit. Down there, you're dealing with cross-encoder re-ranking, rigorous error analysis, balancing crazy latency versus accuracy trade-offs, and running continuous fine-tuning loops. If your system is hallucinating or failing, it's almost always missing a piece of this deep layer, not a flaw in the AI model itself. Think about your classic naive RAG baseline. You take a user's query, convert it into an embedding, find the topmost similar chunks in your vector database, and just stuff those chunks straight into an LLM prompt. Boom, done. It's incredibly fast and it works flawlessly. If, and literally only if, your queries are crystal clear and your documents are completely free of noise. But let's be real, out in the wild, users are messy and enterprise data is incredibly noisy. So why exactly does this basic setup fall apart in production? Well, often the retrieved documents are completely irrelevant because of semantic drift. Or maybe the user's query is just ambiguous, packed with weird domain jargon, or honestly, just a terribly worded typo. Sometimes answering a question means you have to stitch together context from 5 different documents. Or worse, those documents actively contradict each other. And then you have complex questions that require multi-step reasoning, which a simple, flat vector search just fundamentally cannot handle. We need better tools for this. Which brings us to part 2, advanced retrieval mechanics. First up in the advanced toolkit is HyDE, or Hypothetical Document Embeddings. This is a brilliant fix for a very specific, annoying problem, those extremely short 1 to 3 word user queries. Structurally, a tiny query like HNSW doesn't match the linguistic style of the massive, dense document sitting in your index. So instead of embedding that weak little query, HyDE intercepts it and has the LLM imagine what a perfect, comprehensive answer would look like first. The pipeline is super clever. The user asks their tiny question. The LLM generates a fake but structurally rich hypothetical answer. We then take that hypothetical answer and run it through the embedding model. Because this imagined text shares the vocabulary, length, and structure of the actual documents you want to find, it acts like a massive, highly targeted net, pulling in relevant real chunks from the database that the original tiny query would have completely missed. But what if the user is just being super chatty, or vague, or leaning heavily on previous context in a conversation? That is where query rewriting comes in. This pattern uses an LLM to catch the user's raw, messy query, something like, that thing about splitting docs, and rewrite it into several cleaner, much more precise search terms. It is an absolute game changer for conversational interfaces. So the LLM takes that one ambiguous prompt and spins up multiple distinct versions. Maybe one focuses on text chunking in RAG, and another targets document splitting strategies. The system then runs a separate vector search for every single one of those new versions independently. Finally, it merges and deduplicates all those results, feeding a massively comprehensive context window to the final LLM. This right here is the secret sauce that makes conversational AI actually feel smart. Moving right along to part 3, corrective and self-reflective ARG. Say hello to CRAG, or corrective RAG. Naive RAG will confidently feed totally irrelevant garbage to the LLM if that's what the database happens to return, which instantly destroys enterprise trust. CRAG puts a stop to that. It inserts a relevance evaluator that actively grades every single retrieved chunk. If a chunk scores high, great, pass it through. But if it scores low, meaning your internal retrieval totally missed the mark, CRAG is smart enough to pump the brakes and trigger a fallback web search to grab correct, real-time info from the internet before the LLM ever attempts an answer. Next up is FLAIR. This tackles a notorious issue in long-form generation that engineers call the lost-in-the-middle hallucination. Basically, when an LLM writes a really long report, it tends to drift away from the initial context halfway through. FLAIR literally monitors the LLM's confidence word by word. The exact moment the model's confidence drops, like if it gets unsure about a specific metric, FLAIR pauses the generation mid-sentence. It triggers a fresh retrieval query to get grounding context and then resumes generating safely. It's incredibly robust for maintaining high accuracy. Now we're getting into the deep trenches. Part 4, Graph and Agentic Innovation. When a user asks a multi-hop question, where finding answer B depends entirely on first figuring out answer A, standard retrieval just completely collapses. Agentic RAG solves this by acting as an intelligent orchestrator. Step 1, the agent gets the complex query and maps out a multi-step plan. Step 2, it retrieves context for just the first part. Step 3, it might even trigger a calculator or an external tool using that first piece of data. Step 4, only after all those dependencies are fully resolved does the LLM synthesize the final multi-part answer. It can loop, backtrack, and retry until it gets it right. And for enterprise data where the relationships between concepts are just as critical as the text itself, we have GraphRag. Flat vector search is notoriously bad at connecting dots across entirely separate documents. GraphRag instead extracts entities and their relationships into a structured knowledge graph, nodes and edges. At query time, it combines vector search with graph traversal. Sure, it has higher upfront construction costs, but when you need to answer questions about complex, interconnected webs of data, literally nothing beats it.
Bringing it all together, Part 5, the production realities.
Take a look at this comparison, because it reveals the ultimate engineering trade-off. Naive RAG, it's incredibly fast. One LLM call, you're done. But its accuracy sits at a pretty generous 2 out of 5. Now, as you push for that elusive 5-star accuracy, using things like self-RAG or agentic RAG, your LLM calls multiply, and your latency inherently plummets to slow. You simply cannot have maximum reasoning and maximum speed at the exact same time. In production, every single layer you add costs money, burns compute time, and impacts the user's experience.
So how on earth do we balance this? Adaptive RAG is the key. Adaptive RAG puts a lightweight, blazing fast classifier at the very front of your pipeline to score the query's complexity right out of the gate. If the user asks a simple, factual question, it routes them to the fast, cheap, naive RAG path. But if the query is highly complex, requiring multi-hop reasoning or synthesis, only then does it route the query to your expensive, slow, high-accuracy agentic pipelines. It's the ultimate cost and speed optimization trick. Let's assemble all of these patterns into the ultimate battle-tested production stack. You don't just pick one pattern, you layer them. First, you implement conversational RAG to maintain your memory. Then you integrate adaptive RAG to route traffic by complexity. For the tough queries, you trigger RAG fusion to generate multi-query variants for really deep recall. You pass all those extensive results through CRAG to actively grade relevance and trigger fallbacks. And finally, you employ self-RAG right at the finish line to guarantee the LLM's output is strictly faithful to the retrieved context. When you visualize the complete architecture, the data flows seamlessly from memory to routing to multi-query fusion, straight through the corrective relevance check, contextual compression, and all the way to the final faithfulness self-evaluation. It is an incredibly resilient workflow. But I want to leave you with the golden rule of production engineering. While these layers add necessary quality and safeguards, you should never, ever add layers you don't actually need. Build only what your specific workload demands. We've gone way beyond the surface today. You now understand the hidden layers, the structural edge cases, and the exact architectural patterns required to solve real-world retrieval failures. So I'll leave you with this final provocative thought. You know the patterns now, but is your RAG stack truly ready for production? It is time to stop building fragile toy apps and start engineering resilient, battle-tested retrieval systems. Thanks for hanging out with me for this explainer. Keep building, and I'll catch you next time.